Okay, so welcome to the last and final lecture of SEG 2100 for this fall term 2002. We're going to quickly wrap up the stuff on quality assurance and then have a brief overview of some of the topics in the project management chapter. I'm not going to go through the entirety of chapter 11, but we will go through some parts of it that are the most important parts. So far we've been talking about testing, and testing is of course the thing which I said that for an undergraduate student really you need to have more emphasis on. There are plenty of other aspects of quality assurance, and we'll look at one of them in just a few minutes. In the testing process, we generally say that there are a number of different roles. On this slide, slide 57, we have two main roles, developers and independent testers. And the key thing here is to realize that there should be, in any decent organization, an independent testing group. There should be, even if it's a small company with just 3 or 4 people, there should be somebody who is designated to do testing who isn't the person who originally developed the software. And the reason for that is that the person who's got an independent perspective on the software is going to find bugs, is going to think of things that the developers never would have thought of. Okay? So you need somebody who's got an outside view, who hasn't really been involved in the design, so that they can find bugs that the designers wouldn't have thought about more easily. So we still think that developers should do some testing, and you should make sure that your software is reasonable quality. Maybe you should do some white box testing, do a first pass of black box testing rather quickly, just to make sure that the test case is passed, and if you have any doubts about anything, you test it. But independent testing by a third party is what is needed to get that level of quality that's needed for release. We also have testing involving users and clients. You've probably heard of alpha, beta, and maybe acceptance testing. Okay? Beta testing is the one that most people hear of because you hear of beta releases of software. A beta release is a release where you release the software into the user community, and the users end up finding the remaining bugs before the final release. Well, they usually don't find all the remaining bugs. As we said, the law of conservation of bugs says that if it's a bad piece of software anyway, some bugs will continue indefinitely as the software continues to exist. But nevertheless, the notion of beta testing is well established, and often users can find a few things that the independent testers wouldn't have found because the independent testers don't have the same perspective as the end users. The end users are using software with a particular mindset in a particular way. Okay? Alpha testing is similar to beta testing, but it's even earlier, and typically it involves bringing the users and clients into the organization and getting them to test in the development organization's premises. Okay? So it's like you're not really doing your real work with it in alpha testing. You're just trying things out. It's not quite prototyping, because prototyping is typically in the requirements phase. But it's with what is going to be the final product. First step, let's bring them in, test them, watch them closely as they're doing things, work out the kinks. Then we'll go to a beta where we give it to them and say, okay, you can start doing your real work with it, maybe a select subset of the users, and then finally we have a general release. And then there's also a thing called acceptance testing. Acceptance testing is where a client decides whether they want to accept software or not. So if you have contracted with some developers to produce software, when they deliver the software to you, you will typically do acceptance testing, where you test the software yourself, maybe based on your own set of test cases, in order to determine whether you are willing to pay the final payment on the contract. You also would use acceptance testing if you are purchasing software in the open market and you want to say, well, okay, we'll try out this product and this product and this product, and we'll work out which one is the best by running a series of tests to see which one we would accept. Okay, so whereas alpha and beta testing are organized at the initiative of the developers, acceptance testing is at the initiative of the customers, typically. Okay? Any questions? Inspections, then. Inspections are another and probably the equal in importance quality assurance technique for, as I said, quality assurance. Okay, they're equal in importance to testing, and many people feel they should be done even before the bulk of the testing is done. We'll talk about that in a minute. Basically, you have a bunch of people sit down and study the source code, before that the design documents, before that the requirements, the specifications, whatever kind of material you produce as part of the software, you have human beings read it, typically more than one, often in a meeting format. And they do more than just read it. There's a style of inspections that involves a systematic process that teases out bugs we'll talk about. I'm going to talk about a particular style of inspection work that is well recognized in industry. I used this technique and first learned it when I was working at Nortel back in the late 80s. And it's still quite widely used. There are some variants on this now, but this is the core of a good technique for inspecting software that's quite effective. You have a number of people. First of all, you have the author. And we imagine we're doing this in a meeting context. We have the author, the person who wrote the code. If there's more than one person, then multiple authors. And I'm going to talk about the context of code here, although you can apply this to design documents too. You have a moderator, somebody who is going to be running the meeting effectively. You have a secretary, somebody who is going to be writing down the problems, the defects that you find, not an office staff person, somebody who is a software engineer, okay? Because they have to thoroughly understand the technical details, and they're going to contribute to the meeting just the same as everybody else in terms of finding bugs. And you have other people, 1, 2, maybe 3 other software engineers, and we're going to call these paraphrasers. Okay, these are the people who are going to be active at any given point in time going through the code. Not reading it out aloud, but what we're going to say, what we're going to call paraphrasing it. In other words, describing what the code does without exactly reading it verbatim. And that's quite important. This process of saying it in your own words, paraphrasing, forces you to think. If you just read code out loud as you're going through, it becomes completely automatic. I can sit and read something here while thinking about something else, while daydreaming about what I'm going to do tonight. Okay? Whereas if I'm forced to change what's going on and use different terminology, different words, explain it, then I'm forced to think about it actively, and that might tease out bugs. If I'm paraphrasing, I might say, oh, it looks as though the code does this. And somebody else might say, but it doesn't actually say that. Well, okay, so what's the problem? Have I misinterpreted it? If I misinterpret when I'm paraphrasing, it may well be that is in actual fact a bug I've found, or it might be that I haven't understood it because there's bad naming conventions or bad comments or some other source of confusion in there. And so that will highlight things that need to be fixed. Okay? A number of principles of inspecting. We're going to inspect all document types, so code, but also design documents. We're going to have a team of people, between 2 and 5 people typically, to do it. We're going to make people understand what they're inspecting before they come into the meeting. So that it's not the first time people have seen the code or seen the design. They've read through it. They have a basic understanding of what it is. Okay? That means that the meeting will be much more efficient. And finally, we're only going to inspect things that are finished. So when a software engineer finishes writing the code for a class or a set of classes, he or she will then take those and inspect them, him or herself typically, to make sure that the code seems to be good. Typically run them, do a few basic developer tests to make sure that there's no egregious errors, although some people would even say skip that step, and then submit them to the official inspecting process, at which time the moderator would call the meeting and the inspection would happen. And then, typically, it will go to fixing the bugs and then formal testing. Okay? But we're only going to inspect documents that the designer feels confident in. In the defect meeting, we're not going to discuss how to fix the problems. You can sit down and notice a problem and then spend half an hour deciding what the best solution is. That is something which can be decided by the designer offline, after the meeting, or maybe by 1 or 2 people. But you don't need to involve everybody because it's a waste of everybody's time. You're not going to discuss the details of style. You might point out something which is inconsistent and therefore confusing, but if it's purely somebody's used a slightly different naming convention or something, it's typically not something that you would discuss in detail in the naming convention, in the inspection meeting. And you're not going to rush. It may seem surprising, but 200 lines of code an hour is the typical speed at which inspections have been found to work best at. That includes the time spent going through all of the lines of code, including comments, and dealing with the typical defect rates that you would find. So raising a problem, spending a couple of, maybe half a minute determining if it is a real problem, and then recording it and then moving on. Okay. So that's a typical rate. And that means that inspections can actually take a considerable amount of time in the development process. And that's something that has to be accounted for when you're doing this process. Okay. A couple of hours of limit of time, keeping careful logs of the inspections and making sure that each of the bugs is fixed later on. So each of the bugs goes into the problem reporting system. And if you find that you have such a bad piece of software when you're inspecting it, that you have so many bugs and you fix so many bugs, that it's say more than 20% of the code has to be changed, you just go back into the inspection again. Okay? Because you'll typically again find more bugs. The inspection process is typically a process that involves just the developers, software engineers, not the upper management, typically not any management at all. And the reason for that is that if management is regularly involved in inspections, then the managers are going to be seeing who's making defects and using them for performance reviews. And so what then happens is that people say, well, you know, you're my friend, and I'm not going to point out a really bad bug you made because I don't want a manager to see that. And therefore the purpose of the inspection is compromised. What you want is all the really bad bugs to be brought out, and even the little trivial bugs. And so what if the developer had a bad week and did some really lousy code, okay? Well, you know, fine. The inspection will find those bugs. And let's just keep that out of the management's eyes, because the purpose of inspection is to find those bugs. Hopefully the developer will fix the problems. And yes, there is a need for reviewing and understanding on the part of management their performance and how good developers are. But that can be done through other processes. It can be done through taking a look at the test cases and how many test cases pass based on the code that you've developed. Okay, but the inspection process should probably not involve that process, because it just mixes and causes different concepts to be in play at the same time. Okay? So in the meeting, you typically have the moderator calling the meeting, making sure everybody's prepared. Okay? Then each of the paraphrasers takes turn explaining the code, line by line, block by block. Okay? But as I said, not reading it verbatim, paraphrasing, but explaining exactly what it does, even though you're not reading it verbatim. And everybody speaks up when you notice a defect. The person who speaks up might be the paraphraser. The paraphraser says, I'm not sure what this is saying, I think this is a bug I've just noticed. It might be the moderator, it might be the secretary, and it might be the author. In fact, the author will quite often find bugs, because the author is following along and notice the paraphraser saying something strange. I didn't intend that. And then suddenly realizing, well, okay, the paraphraser has said something which is true, but that's not actually what the code is supposed to do. Okay, and therefore notices a defect. And then the defect gets written down. There may be a quick discussion of whether it's a defect or not, but not how to fix it, as we said. Any questions about this notion of inspection so far? Okay. It's important to understand the notion of inspections. Many of you will go into companies and find that there is an inspection process in play. But if there isn't, then your job is to bring this kind of technique into the companies you work for, or the departments you work for, or whatever. Okay? In fact, a lot of the latest software engineering techniques are brought into industry by people graduating with degrees and where they've taken courses in software engineering. Because typically what happens in some organizations, especially smaller ones, especially ones that are working in industries that are not software, so they have a software development group doing various things, but their main business is, say, I don't know, making toothpaste. Okay? Well, you know, they aren't in the mainstream of understanding how to do good software. And so they hire somebody, and that person is coming in with education that can show them some of the newer techniques. So if you find that the inspections are not being done, then you can try and encourage people to do inspections. Or maybe when you become a manager after a few years, you can actually, you know, bring in this kind of technique yourself. Of course, you should always then go and see what the latest recommendations are. See, I'm telling you the recommendations as of late 2002. And inspection concept has been around for a good decade or so, and it probably will remain reasonably steady, but there are going to be plenty of improvements to this and many of the other techniques we've talked about. And so you have to stay up to date. But inspections are certainly not going to go away. If anything, the notion of inspections is becoming more important. People are recognizing that it's as important as testing and even probably should be done first. So here is a comparison of inspection to testing. The key is that they rely on different aspects of human intelligence. Testing relies on this aspect of systematically tracking things down. Okay? It's very much a problem-solving process, a detective work process. Okay? A process of meticulousness in trying things out and trying to break things. Whereas inspection involves in very much a program understanding. How does this program work? Kind of a process. So different aspects. Testing will find certain defects that inspection will never find. It will find defects that are not obvious from the code, things that are obscure, things that involve bits of the system interacting with each other in ways where the bits of code are far apart. Okay? Inspection will find defects where the things that are causing problems are close together, and which might not show up in testing because they might be rather obscure cases. Okay, but you can nevertheless understand that, say, if a certain value was entered or a certain combination of values was entered, that a bug would occur, but the testers might not ever think that it would be necessary to use that combination of values, so that particular bug would never be found until some end user ran into it later on. Okay, inspecting can also find things that relate to efficiency and maintainability. Testing, I said you should do testing on response time and throughput and peak performance and things like that, but you're kind of guessing. Whereas with testing, you can see if an algorithm is clearly going to be inefficient and is clearly going to waste resources. It's right there, and so you can pick those things up right away. And you can also pick up maintenance problems. You can say, well, this code is really difficult to understand, and therefore it's going to be a maintenance hotspot later on. It's going to cause bugs when people try to fix it. And so that should be marked as a defect. Even though it might not give rise to failures immediately, it nevertheless should be considered a defect, because it will give rise to defects, or is highly likely to give rise to defects later on. So bad naming conventions, things that are hard to understand of any kind, should be flagged as defects. Maybe they're level 3 defects, things which could be perhaps left if there's a crunch, but they nevertheless should remain in that defect log, and you should try and get around to fixing them when resources permit. And so the key is that the chances of mistakes are reduced if both activities are performed, if you do both inspecting and testing. And the general consensus these days is to do inspecting first. Basically doing very little. Some people say no testing at all. Just write the code, and the designer inspects it, and then it goes to an inspection of a group, and then you test. And they've done studies, scientific studies, and we shouldn't downplay the scientific studies, even though it's counterintuitive, that in actual fact you save more time in the long run by not testing first. The concept is you're going to have to test anyway, right? You have to test even after inspecting. And therefore, don't test, then inspect, and make changes, and then test again. Just go right to inspecting, find all the defects, and then go to testing. I'm still a little bit skeptical. I think that testing sometimes can be done extremely fast, especially if it's developer testing. And that gets rid of the worst bugs, so that inspecting can find the more deep ones. So there's a bit of dispute about that right now, but we have to follow what's going on in the studies, in the science of this, and see where that goes in the next few years. Okay, so that brings us to the end of our discussion of inspection. A quick few comments about some other quality assurance techniques. Okay, one of them is root cause analysis. Okay, this is a technique that you would use when you detect a failure or an important kind of defect, and you say, okay, let's try and figure out how we got to the situation where we have this defect. Is it because the software developer had a bad day? Is it because the software developer or the testers had a lack of training and they weren't up to snuff and therefore the defect got through? Is it because we're too tight in schedules and we're forcing people to work too fast or too long hours, and therefore they're letting defects through? Is it because our reusable technology is bad? Is it because our architecture is bad? Okay? The concept is that if you pick some important defects and do root cause analysis, and the management then takes action, that's likely to prevent subsequent defects. Okay? So far, testing and inspecting have been sort of looking and saying, okay, let's try and clean up the defects we have. What you really want in quality assurance is to, as well as doing that, to prevent future defects. And the only real way you can do that is by actively keeping track of the defects and analyzing them and trying to take preventive action, not just corrective action. Okay, so that's an important class of techniques that I'm not going to go into in any more detail, but it is something which you would study in a more advanced course. And then there's the notion of continual improvement. There's this notion that software engineering organizations should constantly be trying to improve their process. There are various organizations that have established standards for how to do this. There's the ISO and the Software Engineering Institute Capability Maturity Model. Okay, we're not going to go into those models in any detail, but those are notions of the recommendations for processes that software engineers should follow when they're doing software. And the higher levels of those, one of the recommendations is that the software engineering team should always be trying to figure out how they can improve their quality, how they can improve their time performance to develop software faster, and various other kinds of things. So in order to do this, you need to keep track of things. You need to measure. You can't determine if you're improving or not unless you measure things. So you have to measure things like the failures encountered. Always, all software should be keeping track of the failure rates as detected by testers and by users. In addition to the failure rates, the number of defects. Different number, right? Defects being the bugs, failures being the actual problems given rise to by those bugs. And it's important to track those separately because they reflect different aspects. Failures being the impact on the user, defects being how much work we have to do to fix it. We want to keep track of things like the percentage of code that's reused. We want to measure that and have graphs. A lot of companies will put graphs up on their walls. And it's very interesting to study those and to try and get into the team spirit where you're trying to improve your performance. It's like in a sports team, you know. We had such and such a performance last year and last season. This year we're going to try and do better, okay? And that's basically the concept. Of course, you know, with teams you can have a good year and a bad year. Hopefully you don't have a bad year, but if you improve your coaching, in other words, your management, and you improve your techniques and improve the training of your people, you should get better. That's the concept. Another thing you can measure is the questions posed by users to the help desk. Keep track of all of those and see if your numbers are getting better in that respect. So there's this whole notion of software metrics, it's called. Metrics is measurement of software. We haven't talked about it in this course, but it is a very important concept that in fact, you can have a whole course devoted to just measuring software. Okay? All engineering artifacts have to be measured in some way. And software metrics deals with that. Another quality assurance technique is postmortem analysis. It's a little bit similar to, it has relationship at least, to root cause analysis. Root cause analysis is typically looking at a particular defect or failure. Postmortem analysis is saying when you finish, when you release the project, let's go back and look at what we did. What did we do well at? If we had panics, why did we panic about things? What went wrong? And what did we do well? What can we do again next time effectively? And so, as we're getting ready for the next cycle, we're going to learn some lessons. If you don't do this, what you're doing is you're just struggling on from day to day, to week to week, to month, and not really thinking back and thinking forward. Okay, so postmortem analysis, you might get together with everybody for a day, maybe it's a retreat somewhere. You analyze how you're doing, the techniques you're using, where training is needed, and try and make plans to do better next time. There are a number of software engineering standards that you can follow, and you probably should follow. Standards are quite an important and growing concern in software engineering. All engineering branches have standards that should be followed. In software engineering, the IEEE is probably the body that puts out the most standards. And by the way, I highly recommend that all people in this room consider joining the IEEE. I happen to be the branch counselor here in site in our department. But there's a student branch, and I think everybody should consider joining it because it's certainly it's the international professional, one of the two international professional organizations that software engineers should join, the other being the ACM, which I'm also a member of, by the way. Anyway, the IEEE puts out standards, so do some other organizations. The ones on this page, in fact, are non-IEEE standards. Personal software process is a document that's produced by an organization called the Software Engineering Institute, which is at Carnegie Mellon University, and it's funded by the U.S. Department of Defense, primarily. But it's very well respected as an organization that puts a lot of effort into studying how to do software engineering. And they put out the thing called the PSP, which is a series of techniques that an individual programmer, software developer, can learn to measure and track their own performance. So you can become a better, higher quality, faster developer as an individual. Okay, so I leave it to you to think about investigating that. Some universities integrate PSP training right into courses. I don't do that in my course, but it's certainly something that could be done by other professors, but I don't think we do it here. Some universities do. The basic key is being aware of the defects you make, inspecting your own code, and setting various goals for improvement, and measuring, keeping a log of your performance to do that. TSP builds on that and is a similar concept for small teams. How do you improve the quality work of your team? And CMM, I mentioned briefly a while ago, is a 5-level model for an organization. So organizations by default are at level 1, which means that they kind of do software engineering in an ad hoc way. And then gradually, by adopting a series of techniques, they will move up level 1, level 2, up to level 5. Very few organizations ever reach level 5. If you do, it's great prestige. Okay? So for example, there's a few companies, in particular the group that develops space shuttle software is at level 5 and has been for many years. And there are a few other companies. And for example, there's a number of companies in India are very proud of the fact that they have got to level 5 well ahead of, say, a number of companies in the US. So it's an international thing that is quite well respected. However, ISO 9000-2 is a real international standard. These previous ones are Software Engineering Institute standards, whereas ISO 9000 as a whole is a quality group of standards that are used for industry, any industry. And ISO 9000-2 is the recommendations for software development that are part of ISO 9000. So if you go out on the street and you look at trucks or you look at industrial buildings, you'll often see ISO 9000 certified on them. Okay? And so in any industry you can be ISO 9000 certified, including software. And so ISO 9002 gives a list of things that you should do. It's not 5 levels like CMM. Some people like CMM because it forces you to try and gradually get better and better until you reach level 5. ISO 9000-2 is just a 1-level thing. You're either not there or you're there. I guess it's 2 levels. Okay? And there's lots of details. And I once taught a course where we went into these things in 3 or 4 lectures. But the important thing is to be aware of them. You can always go and look them up and look at the details yourself. Okay? And hopefully these will be brought up in more advanced courses. Okay, now there's a section of test cases which I'm going to skip over right now. I'll let you take a look at those test cases in the book. They follow some of the details that we talked about with their test case numbers and instructions, expected results. I'm not going to go into them now. Just want to quickly wrap up on slide 79 where we have some difficulties and risks in quality assurance. Okay? So first of all, it's very easy to forget things. It's very easy to forget, for example, to test for performance, or to test for peak load, or to test documentation, or to test some particular class of algorithmic defect. Okay? So the idea is that what you need when you're developing tests is not only you go through the requirements, but you also go through a checklist of things to test, just like the checklist we talked about in this course, okay, to make sure that you've covered all the ground. And we also have this big risk where there's a constant tug between let's have high quality on the one hand and let's get this software out the door in the customer's hands on the other hand. And so often shortcuts are taken. Testing is chopped off. And managers say, okay, look, it's got to go to the customer. I promised it to the customer 2 weeks ago. They're going to cancel the contract on us. Or they won't give us the next contract. Or we're going to lose our bonus. Or whatever it might be. It's going to the customer on Friday this week, whatever happens. Okay? And so testing is cut short. It goes to the customer. Customer finds all kinds of bugs, says this is no good, sends it back. 3 months later, it goes to the customer the second time after the testing's done. Or the customer says this is no good and doesn't use it, or whatever. Okay? And so there's no easy answer to this. How do you deal with this kind of problem? Because there really are hard deadlines in many cases. And so what you need to do is you need to have a process in place that is aware of this tug of war between these two, the high quality and the deadline issues, that is managing the process, that is keeping track of the quality levels that are being achieved as different parts of the system get tested. Typically you have a separate quality assurance department that can be promoting the quality side, because typically the line management is promoting the deadline side. That's typically the thing that first comes to their mind. You have quality statistics published so everybody can see them. Everybody knows how the system is shaping up. And you have competent project management where people really understand the time. They're doing risk management. They're adjusting the project plan as needed as the deadlines approach, so you don't run into this crunch where you have to chop testing off. It's just unfortunate that testing is the last step. That's what gets chopped off. I mean, you couldn't chop off coding. You couldn't do it because you wouldn't have a system. But you can chop off testing, and that's what gets done. If coding was the last step, you could test before you coded, then hey, you would never have this problem because you just can't deliver something. You shouldn't deliver software that's not tested, but the only way you can deal with that is to carefully manage the process and make sure that you do have enough time to test. And then we have to realize that people have different levels of skills. Some people are really, really good at testing and maybe less good at architecture or less good at user interface design. Other people might be really, really good at requirements analysis, but when it comes down to testing, they don't find the bugs. They just sort of don't have the knack for that. And so it's really a good idea to understand and get a sense of what people are good at and have people specialize in those things that they're very good at. It's also a good concept to shift people around. When I worked at Nortel, I was lucky enough to be, I started off in development, okay, worked in development for a year or so. And then they said, okay, you're going to do a 1 month rotation in an independent test group, okay? You're going to come back here later on, you're going to go 1 month in an independent test group. So I went into an independent test group testing a different product for a month. And that taught me a lot about how to be a better developer. I could see, I was working on the other side of the fence, working to improve quality, working to report bugs. I became somewhat vicious at finding bugs that other people hadn't found and realized I had a bit of a knack for that. But nevertheless, when I went back to programming again, when I went back to designing again, I realized a whole types of defects and whole ways of thinking that I hadn't thought about before. Okay, so having an experience in that other side is often a good idea. Okay, any questions about quality then? All right, well, in that case, we will shift right away to the project management chapter, and we'll go through some parts of it. This is the last chapter. Not the last chapter in the book. There is a review chapter, chapter 12, which summarizes some of the important things, but it's the last chapter that has new content. By the way, for the exam, we'll be relatively light on chapter 11. Maybe one question, small, obvious question in chapter 11. Okay, but up till chapter 10 is where you should put more effort. And certainly the chapters focusing on design issues, 5, 6, 7, 8, 9 are going to be the heavier weighted ones. Okay, just to give you a concept on that. So, managing the software process. It turns out that most software developers, probably more than half, will at some point have some kind of management role, whether it be formally project manager, or whether it be leading a small group of people at some point in their career, where you have to do a certain series of techniques. And these techniques involve things that are listed on slide 2 here. So, for example, deciding what needs to be done by whom, estimating costs. Cost estimation is a key technique that we talked briefly about in the design chapter, where you're estimating the costs of a particular design decision. But here, we're talking about estimating costs globally of the entire system. Ensuring you have the right people, okay? So finding people, hiring people, or choosing people from elsewhere in the organization, and making sure people are doing the work that they're good at, okay? Defining responsibilities, exactly what you're going to deliver, okay? And what objectives in terms of productivity you might meet. Scheduling. When are we going to deliver things? When are we going to meet to decide on the design? When are we going to what is our delivery deadline going to be for various releases? Making arrangements, making sure that people have the appropriate software, hardware, reusable code, etc. Directing, which is basically the process of issuing commands and orders, etc. Being a technical leader, so when people come to you and say, I have some questions about architecture or what new software engineering techniques we should do, you can help guide people about that. Reviewing and approving decisions. So you might have some architects, some user interface designers, some database designers. They're making some key decisions that are going to impact the entire system. The project manager needs to be there to coordinate and say, yeah, I think that's a good decision, or we should perhaps consult with some other people. Okay? Building morale and supporting staff, making sure everybody feels good so that they're productive and their morale is good. Monitoring and controlling, keeping track of where we are, knowing what our defect rates are, knowing whether we're on schedule or not. Okay? Interacting with other projects, with other managers, with client managers as well, writing reports for the clients and for other managers, and trying to do this continual improvement process we just talked about, trying to improve the process continuously. Okay? So that's basically what the project manager does. And in the software engineering program, there is a course in 4th year that focuses on all of these activities in some detail. Okay? And so the computer engineers don't get that. You might be able to take it as an elective if you have the right sequence. Software process models. Okay? These are models of how to do a software project in the large, okay? There are a number of general high-level strategies for doing a software engineering project. We briefly alluded to some of these in Chapter 1. We're going to talk about them again just briefly here. These are fundamental overall approaches to software engineering. And choosing one will help you to manage your project effectively. As it says here, that should be seen as aids to thinking. It's not that you do things bang, 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 precisely following one of these. These give you guidance as to how to make your own unique plan that's tailored to your own unique project. The first one, which is not good, is the opportunistic approach. Okay, this is the approach which is almost the default if you don't do any project planning. Okay, you cook something up, call it a first prototype. You modify it until somebody's satisfied. Might be just you, might be a user, which is actually quite good, but typically it's just you. And then you think of some idea for improvement, you hack some more stuff on, and you go back and you modify it until it works, and you hack some more stuff on, and you just keep doing that until you decide to stop, or until the project gets cancelled, or until the customers don't come back to you with any more requests, or whatever it might be. Okay? So we want to try and improve on this model. This is the baseline. The baseline model is just keep working and keep adding things. Okay? And it has a number of important defects. It doesn't cause you to think about the importance of requirements. It just basically leads people to think of code, fix, which is bad. And you end up then with not doing design, and so you have code that deteriorates as you keep hacking new things on. There's nothing to aim towards. You don't have any goal. You're just working, making changes continuously without a goal. You don't know where you're heading. You don't know a level of quality or a level of size or a particular set of requirements that you need to complete. You have none of that, and therefore you don't know whether you're doing well or not. Okay? So the processes we'll talk about in a few minutes give you a systematic way of thinking that will improve upon the opportunistic approach. The old classic is called the waterfall model. It's an old classic, and I emphasize the word old, because in today's world it is not considered to be the best way to do things. And in fact, we'll basically say you shouldn't do the waterfall model in a pure form, although it does form the basis for many of the other approaches. So in the waterfall model, in the classic waterfall model, you have a project to do. You figure out the requirements first. Maybe you look at other diagrams like this and they say you do the feasibility study first or something like that. But basically, you do some upfront work that basically culminates in having the requirements. You might move down into a more detailed level of specification. And at each step, ideally, you're going to do verification and validation. So you're going to make sure your requirements are good. Once the requirements are good, you can do some more detailed specification. You make sure they're good, verification and validation. And you do some design. And then, once you've done the design, you do the implementation. You code it up. And then once you finish the coding, which involves V&V testing, you integrate and deploy the software, and then you maintain the software. And by the way, at any given point in time, you might find problems. So while you're designing, you might find problems that require going back and fixing the specs. And that's what these back arrows are. When you're doing implementation, you might find problems that force you to go back and fix the design. But fundamentally, it's step 1, 2, 3, 4, 5, 6, and then we maintain it. And that maintenance process is the longest process, and it goes on until the software is finally retired. Okay, so that's the classic approach. And it has a number of very important problems. Okay, but let's first of all talk about some of the positive things on slide 8. It says that you should work in a series of stages. That is, it's good to think about stages in many respects, okay? Rather than just we're working on and on indefinitely. The stages to think about. That's a good way of thinking. It also says that you should do a quality assurance step before moving on. So you shouldn't just push stuff out the door and hope for the best. You should make sure that when you finish something that it's of good quality. So that's good too. And it also recommends that sometimes you need to think by moving back to previous steps. So these are some good things about the waterfall model. However, it has some important problems. Okay? One of them is that it says you've got to completely finish, or it implies, if you look at the diagram, you've got to completely finish one step before you can move on to the next. So I've got to completely finish my requirements before I can even think about the design. Okay? Then I've got to completely finish the design before I can think about the code. Now, that is inefficient in a number of ways. One reason why it's inefficient is because, let's say I have to finish the design before I code. That means that maybe you have some people who are going to be focusing on implementation. Well, they've got to wait for all of the entire system to be designed. That doesn't make much sense. It might be better to have some people get right into the implementation when part of the design is ready, part of the design of some subsystem. Okay? It also doesn't let you think about prototyping. Okay? It isn't implicit in this model, or it isn't explicit in this model. And finally, and probably the worst one, okay, it doesn't suggest that it suggests that maintenance is just the entire thing is finished and we're just going to sort of fix bugs and make minor changes from that point on. In reality, software doesn't work that way. In reality, you have a continual process of making major changes called releases to software. And it's not maintenance as an entire process that goes on forever. It's really a whole series of separate projects. Okay, that's really what happens. So the waterfall model tends to lead managers to think in ways that are not ideal, such as the maintenance is everything beyond the final release. And so people have come up with different styles of diagrams. One of them is the phased release model. The phased release model is adding a few improvements. It's still got some aspects of waterfall, step, step, step. Still got the V and V, so it's still got some of the good stuff. But now it's saying that instead of just one big process where the entire system is required, develop the requirements of, the entire system is designed, entire system implemented, entire system maintained, we're going to divide it up into phases. And we're going to have one phase first where we design and implement that phase, get it out to the customers, then move on to the next phase. Maybe we still do the entire requirements in one block, but then we release it in stages. So this is an improvement over the waterfall model in most systems. We get stuff to the customers early, among other things. Okay, and so the key is, as it says on slide 11, each phase can be released to the customers when ready. So customers get to see something earlier, and that means that they'll also give you back feedback earlier. Okay, if there's big defects or big problems, they're going to be able to tell you earlier. A lot of systems have failed in the following way. They've been developed for 4 or 5 years maybe, from requirements to implementation. Finally, the implementation is complete. Everything is perfect. Then it goes to the customers. And the customers say, oh, all kinds of problems, here, there, and everywhere. Okay? The entire system is rejected. And you have to spend another 2 years fixing it up, or you scrap the entire project, as sometimes happens. That has happened, 4 or 5 years of work, goes to the customers, everybody thinks wonderful, and then the customers trash it completely. Or the users do. Phase release model mitigates that risk by saying they're going to get something early on. And if there's problems, we'll detect it that much earlier. However, the model still says that requirements have to be developed early, and that's still a bad idea. So we move on to the spiral model of Barry Boehm. This model says that basically what we have is we have a series of concentric spirals that get bigger and bigger and bigger. We start in the center, we develop a prototype, and each time we go around the loop, we're going to be following the same sequence. So our initial thing is analyze the risk of the system. He always says risk analysis is integral in every loop. What things could go wrong, what things can go right. Develop requirements for this first prototype. Specify it. Do some design. Implement it. Deploy it to a bunch of people who are going to be playing around with it maybe. Review the results. And that's your first prototype. You do the same thing for release 1, release 2, release 3, release 4. So effectively what we've done is we've taken these waterfall steps and we've put them around this circle, and we're going to be going around this circle over and over and over again. And the first few times around the circle are prototypes, and then we have real releases. Okay? And each release is going to follow the same process. So the concept of maintenance vanishes out of this model. It's just a series of releases now. And this is considered a much better way of thinking about software development in general. But there are still some improvements we can make. Slide 13 does show a list of these benefits, some of which I've just talked about, so I won't go into it in any more detail. The evolutionary model is a diagram that I drew, which helps to explain the fact that these spirals overlap with each other. So if you think of these little humps as one iteration around the spiral. In the pure spiral model, it looks as though you're finishing one and then starting another. But in actual fact, if you think about it, you're going to be starting work, ramping up until you're working at a high speed, and then you're going to be ramping down. As you're doing the final stages, as you're doing the testing and the deployment, you need to, at that time, be starting thinking about the requirements and design of the next release. And the next release might be bigger. And so the size of the hump says how big the release is. And also, this diagram shows the time. And so you can actually put these things you can put a time scale on and put actual months underneath these things. And I find that that's a better way of visualizing things, because people really like to think in terms of time. Okay, so this is my model. It's not fundamentally different from the spiral model in many ways, but I think it's just a different way of looking at things that might be useful for people to visualize the process. So the waterfall model still underlies some of this in some ways. We still have sort of mini waterfalls following each of these humps, except the maintenance is gone. The maintenance is just the next release and the next release and the next release. So each of these phases is, as I said, like a little mini version of that phase, except that we still embrace the notion from the spiral model of risk analysis at the beginning and review at the end. Any questions about these models so far? Remember, your job as a project manager or team leader is to pick the model that works best for your system or your subsystem or your team. Okay, and mix and match, understand the pros and cons, and come up with a project plan that follows one or more of these styles. Another model, it comes out of other branches of engineering, and it's not a different model. It can be used in conjunction with these previous models, called concurrent engineering. Concurrent engineering is the first few phases. You plan the system, and then you divide it, and the planning can involve requirements analysis, high-level requirements analysis. Then you divide it up into chunks that are going to be completely independently developed. So somebody goes off and develops the hardware, somebody else goes off and develops one software system, somebody else goes off and develops another piece of the software, and they're done completely concurrently with each other by different teams. Obviously, there has to be a well-tuned, well-understood API in each of these, a well-understood hardware interface, so that later on you can come and integrate these things together. And each of these pieces of work on component or layer A, can be done, say, following the spiral model, with an independent team working with slightly different deadlines and schedules. The only core deadline is the one at the end of the release, when they want to come together to integrate things. Okay? So it's just another way of thinking about things that's worthwhile incorporating in your vision, and a lot of other branches of engineering will work this way. If you see people building buildings, for example, doing civil engineering, I find it quite amazing how they're able to work so fast to put together such complex artifacts. And then a lot of the mystery, a lot of the magic of building buildings is the scheduling, is the process of designing the thing concurrently, bits of the electrical system designed concurrently with the plumbing system, concurrently with the structural system. They all come together to the group that's deciding on how we're going to order the parts and get them delivered to the site at the right time, and everything's done with people working concurrently, hundreds of people working concurrently. So there's a lot of science and a lot of management technique in there that we can think about adopting in software engineering. Okay, so how do you choose the process model? Well, slide 18 will show you some of those thoughts, some of the things that is good. So waterfall model incorporates the notion of stages. Okay, the stage notion still exists in the other models, except that now we have little micro stages in the spiral model, where we're going to go around the stages many times. Each of the other models incorporates other positive things that we can think about. Another thing we need to think about as part of our project planning process is re-engineering. Sometimes this needs to be thought about outside of the scope of projects, and it's considered as a separate type of project, where we've had a system that's been in use for a while, it's undergone a lot of changes. We need to go and fix the design. We need to go and take part of the design that's proving bad and replace it with a better design. Okay? So cleaning up the code, making it more readable, replacing parts, refactoring. The notion of refactoring is something which is becoming quite popular and very important in software engineering, and that is taking, for example, a class hierarchy and changing it so that it follows better rules, gives you better polymorphism, better coupling and cohesion, for example. Okay. Cost estimation, then, is one of these key techniques. I'm going to give you a brief overview of some of the core thoughts about how to do cost estimation. Again, it's a major topic, but everybody should have a baseline understanding of what you have to do if you're going to estimate costs. First of all, we have two things that we're interested in estimating. One of them is elapsed time, and the other is development effort. Different things. Elapsed time is the clock time. Okay, development effort is the amount of work. Okay, so if I have one person working for 12 months, well, I have an elapsed time of 12 months and I have 12 person months of work. Okay, if I have 5 people working for 12 months, okay, that's different. Then I have 60 person months of work, but an elapsed time still of 12 months. Okay, it's the development effort that costs us the money, and it's the elapsed time that causes us to make or break deadlines. And so both of them are important. Development effort is usually the most important aspect of cost. Usually the cost of things like the software that we reuse is relatively minor. Not always, but usually relatively minor compared to the human labor that it goes into the development of the system. The labor in terms of the project management's time, the software engineer's time, the tester's time, the office secretary's time, and so on. And we typically measure the effort in software strictly in terms of the amount of time that our software engineering team members take, weighted. Okay, and we do a salary calculation. So let's say, for argument's sake, that you hire a software engineer, a top-level software engineer making $80,000 a year. Okay? Well, you would calculate their time not based on $80,000 a year, but let's say based on $150,000 a year, or even more than that. Accounting for the fact that if you hire somebody to do work for you, there's going to be more work for the managers and the human resource people. They're going to require office space, which requires rent or other payments and utilities. They're going to require a computer that will have to be replaced regularly. They'll require software that will be replaced regularly, and so on. And so we weight the cost of a person based on all the other resources they require. But when we're measuring the amount of time and cost the software takes to develop, we use this weighted time. Or this, and so it's this so-called weighted average cost or burdened cost that becomes how we measure the cost of developing a piece of software. So if this person who we pay $80,000 is going to spend a year to develop on their own, which is somewhat unusual, but on their own, this piece of software, then we say, well, the cost of developing that software is going to be $150,000, $160,000, even though we're paying them only $80,000. Now, if we hired 2 people, okay, both at $80,000, then we would say, okay, well, now the system is going to cost us $300,000. So we multiply the amount of time by the weighted salary that the person accounts for. So that means that from now on we can think about estimating costs strictly in terms of developer time, and then we can convert that to dollars easily later on. So how do we go about doing cost estimation? Well, there are a number of principles we can follow. The first one is the same first principle we applied for design: divide and conquer. We're going to divide up the system and separately estimate the cost of each one. How much time will this subsystem take? How much time will this one take? How much time will that one take? And then we're going to add them all up later on. Okay? If we're doing it in layers, it's how much time will the database layer take, how much time will the functional layer, how much time will the user interface take, how much time will the testing take, how much time will the deployment take. Add all these times up, but the key is to estimate each one individually. You can't just do a big bulk estimate. You've got to break it down into smaller and smaller components where you can realistically get an understanding of how much each one will take. Okay? Then we have making sure that you include all the activities. Okay? Don't skip things. It's quite often that people will forget activities when they're estimating costs. So make sure you consider your prototyping time and your design time and your requirements time. The ones that are often forgotten are the inspection time, or the testing time, or the debugging time, or the documenting time, or the deployment time. Okay? Often managers will just think in terms maybe just of requirements and coding, and that's it. But that's clearly only a small fraction, in fact. In fact, the total time can be much, much more than that. So you've got to separately estimate each of these as well into your estimation process. Base your estimates on past experience. Go back and look at how much time these various things took in previous projects. Get an idea for that. If you estimated previous projects and your estimates were off, well, fix your estimates this time. Okay, that's why measurement and metrics are very important. You've got a history of how much time things actually took. That'll help you to fix your estimates next time. You can use personal judgment to make estimates. In other words, by just looking back at your previous estimates, understanding where you underestimated or overestimated and adjusting. Or you can use some what are called algorithmic models that are talked about in the book in some detail. Algorithmic methods are methods where you systematically estimate the development effort based on industry-wide studies of how long it takes to do various kinds of things. Some of these techniques are based on the number of use cases, so you do use case development, and then you analyze each use case, and it gives you an estimate of time early on. You have to refine that as you get down into design, of course. Some are based on aspects of requirements. There's a thing called function points that analyzes the requirements and gives you an estimate of time based on industry-wide experience. Of course, it might not apply to your system quite so accurately, but it's still better than nothing to do this. Some are based on the number of classes in the domain model. Some are based on the number of lines of code. But the trouble with estimating based on lines of code is that you don't know how many lines of code you're going to get until you've done it, right? So you still have to guess the number of lines of code. So there are models that say, well, okay, if you have 1,000 lines of code, it'll take you this many person months to develop it. But your lines of code estimate might be a random guess. So they're a bit weak. And typically what you do is you use, say, for example, the number of use cases first to estimate the number of lines of code. And then from there you can use other models, other algorithms that are well studied to estimate the final time. I want to emphasize one thing, though. All of this is estimating. It's not bang on, accurate. Here's exactly how much time it's going to take. And in software engineering, probably more so than any other branch of engineering, estimates tend to be more inaccurate and harder to make precise. Because in other branches of engineering, if you're doing civil engineering, you know what the bridge is going to look like. You can quickly visualize all the things you have to do. An engineer can do an analysis. And most of the work is in the construction. And that can be very precisely estimated because the construction techniques, we clearly understand how much time it takes to do various things. And you can still be off. Okay? This building we're in now, they were a year over budget on their deadline and double their budget. So as bad as any software engineering project. But in general, other branches of engineering are more accurate because they estimate the design phase is the least costly phase. The construction phase is the expensive one, and that's what they want to get accurate. In software engineering, the design phase is the costly one. The construction or the distribution phase, the phase where you take the design, which is the code, and you spit it out into CDs and install it in people's computers, is a lot less expensive. Okay? And so the design phase is where all the uncertainties are. We mentioned that in the first lecture. And that's why there's so much more emphasis on cost estimation and project management in software engineering programs and courses than there is in other branches of engineering, because it is that much more difficult in software engineering for a system of similar human workload. Okay. Now, there are massive civil engineering, mechanical engineering projects. I'm not saying that all software engineering is more complicated than all, say, civil engineering. All I'm saying is that for a given size and cost of project, the difficulties of getting the estimates right in software engineering tend to be harder. One of the algorithmic models is the Kokomo model. Here's an example of the formula that is used. Okay, so we've got various parameters A, B, and C that we plug in based on various aspects of the system. I'm not going to discuss this in detail. I will leave that for another course. You'll notice that it is a model which is exponential, which reflects the concept that software systems, as they get bigger, they tend to grow exponentially in cost. They don't grow linearly in cost. And so a system that is twice as big doesn't cost twice as much, it costs substantially more than that. And that's bad. And that implies keep your system small to stop it from running out of control. The function point model is a model that weights together a number of factors. with a number of weights, the W things, and gives you a size estimate in units of function points that you can then convert to lines of code. Okay, so these are things that you will learn about later, but right now the important thing is to understand that these things exist, and that if you end up doing estimation, you should learn about these techniques. So principle 4 for estimation is to realize that there are many differences from project to project. Just because you can estimate one project right doesn't mean you can estimate another project right. Different people will perform differently. For example, it's well known that there's a huge range, a huge scale of abilities among different software developers. One person might be able to program to a good level of quality in, say, 5 days. It might take 50 days for another person. There's known to be a 1 to 10 level of difference in abilities of people, in range of abilities of programmers. Okay? You have your really, really top sharp programmers and your sort of programmers who really don't have much of a clue, all working out there in industry on a 1 to 10 level of productivity. Okay? And you all probably know where you lie, and many of you are probably nearer the top end, but probably very few of you are actually at that top end, because there's just whizzes out there that, like, sort of the Einsteins of programming, you know. They're few and far between. There are a few of them around. Every now and then you run into one and you realize what a whiz that person is. So there are differences in process and maturity levels. If you're in an organization that does things in a very ad hoc way, doesn't measure things, doesn't do much quality assurance, it's going to take you longer. Okay? So these overhead activities, such as doing quality assurance, measuring things, careful management, they take time, but ultimately, once you've done them for a while, your organization will be able to do projects faster. Yet getting new techniques into place can take extra effort initially. But once you've got these techniques established and running, people know how to do the techniques, you typically will find that the cost will be less. Unfortunately, a lot of organizations never get to that stage of introducing these management techniques and quality assurance techniques because they just can't get over that initial investment it takes. A lot of things take investment, and this is one of them. Different types of customers and users. Oh boy, if you have a bad customer, that can take you 10 times as long to get things done. I was talking to a friend last night who has a bad customer. He's doing a private consulting work, and this customer is just constantly changing his or her mind, constantly requiring new things, constantly saying, well, I'll make my mind up tomorrow, you'll have to wait. All kinds of stuff like that. Okay? So if you have bad customers and users who don't want to participate or can't participate, that's going to slow the process down. Conversely, if you've got customers and users who are very active, very knowledgeable, that'll speed it up. And other things, different technologies. Okay, so if you're using Java and other languages that tend to be less bug prone, much faster. If you're using assembly language, C, C++, quite a bit slower, because you'll have more defects. And you have to spend more time being careful about things. And different domains. If you're working in a domain which you know very well, that'll take you less time. If you're working in a new domain, or a domain which is intrinsically complex, you're dealing with complex mathematics in your programming, or complex business rules, that'll take you more time. If you're working with something that's more mundane, it'll take you less time. So you have to factor all these things into your estimates. You have to anticipate the worst case and plan for contingencies. So it's all very well coming up with an estimate that says we're going to get this done in 5 months. But you also need to say, what could go wrong? Okay, A, B, C, D, E, F, and G could go wrong. And if all of those go wrong, it'll take us twice as long. So that's our worst case estimate. Our best case estimate is if I can manage to hire one of these top gung-ho programmers, and I can get the thing done in 2 months. Okay? So you need to give a range of estimates. You need to pinpoint what you expect, but you need to be prepared for the worst case and tell your customers that there are some things that could go wrong and that you shouldn't sort of bank your entire company on this deadline. Maybe things will go wrong, and then you keep updating the estimate. You keep informing your customer as to how things are going and adjusting the estimate on a weekly basis, so that they are aware of whether you're meeting your original estimate, whether you have to adjust it back a bit. The worst thing to do is to adjust your estimate at the last minute. That's often what happens. Okay? We have an estimate that says we'll deliver in 5 months. 4.5 months, you come along to the customer and say, the customer thinks it's going to be 2 weeks away, and you say, oh, by the way, new estimate, another 5 months. Well, that looks really horrible to the customer, because the customer thinks that you've done nothing, you know. It was 5 months originally, now it's still 5 months. So you've doubled your estimate because a whole bunch of things went wrong. But if you've been telling the customer all along, initially here were some risks we anticipated, and some of the risks didn't come apart, some of them did, and you have to extend your deadline, and you tell them that every week, they still won't like it, but it's a heck of a lot better than suddenly announcing at the last minute that, by the way, they're not going to get what they expect. Okay? So I suggest that you do a range of estimates and make sure that you do a pessimistic estimate, and make sure that you identify those things that will give rise to that pessimistic estimate. I also suggest combining different approaches to estimating. So you will combine an estimate that is done with one of these algorithmic models with an estimate that's done by a couple of other experts. And you might find that different people give completely different estimates. And then you say, well, why is that? Well, the reason might be because the different people have thought of different problems or different solutions. And then you can bring them all together and say, okay, now let's figure out, with all your different ideas, what the real estimate should be. Okay, and they can all bring their different ideas onto the table at that point. There's a technique called the Delphi technique, which is basically designed to do this process of bringing estimates together iteratively, which is described in the book. You refine and revise estimates as the work progresses. I mentioned that a few minutes ago. You don't just make an estimate and then stick with it. You constantly change. So there has to be some manager's role whose job is basically doing nothing but managing, and key part of their job is revising the cost estimates, keeping on top of things, understanding what's going well and what's going badly, what new ideas have come up, what changes are coming up, and how they affect the estimates. Update the estimates. If you have a spreadsheet or a project management program, you can do that with tool support very effectively. Okay? So those are the 7 principles of cost estimation. Any questions about that? Okay, I'm going to wrap up very soon, but I want to talk about a couple of other concepts quickly. Software engineering teams. Major structures for teams are diagrammed at the bottom of this slide, slide 30. One structure is called the egoless team. That is a team where everybody in the team is acting as a peer. They're working together, they're all equal, they all might have their own strengths and weaknesses and working on certain particular sub-areas, but they're all working together. And they're all communicating with each other. They get together at meetings all together. Okay, nobody is leading the team, per se. They might lead in their areas of expertise. Okay? That works in very small, very highly technical projects. And one of the problems is because everybody's got to know about what everybody else is doing, there's lots of lines of communication here. Notice all these connections. Everybody's got to know about everybody else's business. The chief programmer team, which I'll talk about briefly in a second, is an approach where you do have a leader, but this leader is not a manager who's dictating things. It's like in an operating room. You've got a surgeon who is in charge, but other people are also in charge of their own area. And there are fewer lines of communication established, as is shown in this diagram, but nevertheless, there is somebody who is leading almost as a peer. Okay? So it's not a project manager that's leading, it's still a project manager somewhere else who's doing cost estimation and things like that, but they're perhaps also a peer in the organization. And then you've got the strict hierarchy. The strict hierarchy sort of reminiscent to the military. You've got a boss who says, okay, you do that, you manage that. And this second manager then says, okay, here's my underlings, you do this, you do this, you do this, report back to me when you're done. Okay? Very militaristic, and little collaboration. Doesn't work so well because you end up finding that people don't communicate with each other enough. Although in very large systems you do have to have a certain amount of this structure. So in small innovative systems, egoless structure can work. Very large systems, you have to have more hierarchy. Chief programmer might be an approach that will quite often work well. Okay. I'll skip the next few slides. I think I've mentioned about those concepts well enough. How big should a team be? Generally speaking, there are in the project management literature, there are ways of estimating how big a team should be. Given the amount of work, given the deadline, you can estimate how big the team should be. And if the team's bigger than that, you're going to waste time. If the team's smaller than that, you're going to be struggling. Okay? So there's often is an optimum size, and these algorithmic models we talked about will help you find that size. One of the things that's well known, it's a well understood piece of software engineering wisdom, is that doubling the size will not help you get your work done faster. Okay? So let's say that I have a project and I have 3 people and it's going to be delivered in 6 months. And I say, okay, well, I'm going to have 6 people and I'll get it done in a month and a half. It just won't happen. It might still take you 3 months. And now you've got 6 people working for 3 months, so you've doubled your costs without halving your time. Okay, it might take you slightly less. It might take you 2 months. But you're not going to necessarily get back the total amount. You're not going to get the thing done in half the time. And the reason why is because a lot of time is spent discussing things and communicating. And now there's 6 people to talk to each other instead of just 3. And so a lot of overhead is lost in that wasting time. Okay, final things I want to talk about. As I say, I'm not going to cover all the slides in this chapter, but I want to just introduce you briefly to a couple of very important diagrams that are used in software engineering so that if you go out into the industry and you see them, you'll understand what it's all about. The first is on slide 38. It's the PERT chart. PERT chart is showing tasks. Okay, these are particular activities assigned to particular people, and the dependencies among these activities. And so, for example, if you look at this diagram, you see it says requirements gathering. 7.5 weeks, 3-person months. This is the elapsed time estimate and the effort estimate. Once that's done, you can then move on to specification. You can move on then to design. You can move on then to a number of things. Implementation of the UI layer, the network layer, the functional layer. Okay, so we're using a phased release approach here. And each of those can continue independently. There are some dependencies between those activities. Notice that specification also, once you've done that, you can move on to the test plan. So the test plan can be done in parallel. And then once the test plan is done, you can then do unit testing. So unit testing is dependent on both the inspection and the test plan both being finished. Okay, so these are the dependency links. Now, I'm not going to go into the intricacies of the PERT chart, but it is an extremely important management tool because it shows you the dependencies. It shows you that if I, for example, miss my deadlines on things in some paths, that will hold up things that are subsequently in the path. And the shortest path, possibly through the system, is often shown on these diagrams. Here I'm showing it as a bold line, which is shown, the bolder arrows here. It's called the critical path. And if you are held up in any of those tasks on the critical path, your final deadline won't be met. A very important management technique. You'll see this in many companies. They sometimes post them on the wall so you can see where you are and what you're supposed to be doing and how you impact what your tasks depend on and who depends on your tasks. Okay? And the final type of diagram that is also very important you'll see widely in all the project management techniques, and it's used practically everywhere, is the Gantt chart. Very simple chart to understand, and you should typically always create one if you're doing a project of any complexity. It basically shows time moving from left to right. In this case, we've calibrated it on weeks, and then the various activities that we're going to be doing, the same activities, the same tasks that showed up on the PERT chart, but now we're laying them out with start point, end point. We can lay these out according to when we plan to start, when we plan to end, and later on as we miss deadlines or as we get things done early, we can adjust those start points and end points and shift these lines backwards and forwards. So diagrams like this then give the team members and the managers a glance at how we're going to manage this entire project, and just like the software architecture, they give us a global view of things. In this case, a global view of the management, whereas the architecture gave us a global view of the design. Okay, I think we'll leave the course there at that point. Are there any final questions anybody has about any of the things we've talked about? Okay, well, good luck on the exam, and as I said, if you have any questions for me, you can bring them at any time. Anybody who's watching the video, if you have any things that you saw on the video, you can send me emails, and I'll try and answer them or direct you to the relevant sections in the book or to other literature. Okay? Great.